metal systems, non-metallic systems, we have talked about it, what are the properties of them, we talked about it. Then we went to glasses, we talked about glasses, how the glasses are made, particularly the metallic glasses, we are more concerned about the metallic glasses. Then we looked at the various criteria for making the glasses, what is called the glass forming ability, we talked about glass forming ability, how some kind of systems, some kind of alloys can easily become a glass, whereas some alloys do not become a glass. So, we looked at various conditions under which we can get a glass. Then we also talked about what are called bulk metallic glasses. So, how to make these glasses in a bulk form, not just the ribbons, which were the initial materials which were made when 1959 Paul Dewey has discovered this particular technique called rapid solidification processing. So, we talked about how a bulk metallic glasses are made and under what conditions an alloy can give you a bulk metallic glass, that also we talked about, various criteria for formation of bulk metallic glasses we talked. Then we went into another class of materials called quasicrystals. We talked about what are quasicrystals, under what conditions you get quasicrystals, and looked at a few examples of quasicrystals. And today what we will look at is what are called nano quasicrystals. How to get quasicrystals in a nanocrystalline form, that means fine quasicrystals dispersed in an amorphous matrix. Okay. These are nothing but like composites. So, you have an amorphous matrix. We have talked in the last class that when you take a glass and crystallize it and get nanocrystals in it, then the properties can be improved. We have shown that the mechanical properties can be further improved by just dispersing nanoparticles in a matrix of amorphous phase. So, we will try to see how these nano quasicrystalline particles can be embedded into an amorphous matrix and under what conditions we can get such a thing, and what are the systems which can lead to this kind of nano quasicrystalline materials in a amorphous matrix. So, to go about it, we should first see where this whole field has started. Long back in 1996, Koester is a person from Germany who reported that when he took a zirconium copper nickel aluminum alloy and then took that alloy, rapidly solidified that alloy, he got a glass. And when he started heating this glass, he saw that it undergoes crystallization in basically two stages, and in the first stage of crystallization, this glass gives you what are called nano quasicrystalline phases. That means quasicrystals come out in a very fine form, uniformly distributed in a matrix. But the problem was that in almost similar years, 1999, within 3 years after that, in Japan, another group which is called Inowe's group, Professor Inoue in the Institute of Materials Research, Tohoku University, he took the same alloy, but he could not get the same phase. He took the same alloy, could make a glass out of it, and he tried to crystallize, and when he crystallized it, he did not see any two-stage crystallization, but he could see only one-stage crystallization, and the product of that crystallization was a crystalline material, but not a quasicrystalline material, and also the crystals that were obtained were big crystals, not even nanocrystals. So, the question here was that why this particular alloy could give a nano quasicrystal, why the other alloy with the same composition could not give, just the only difference is one was made in Germany, another was made in Japan. Okay. Does it differ the formation of various phases? If it should change from country to country, obviously there is no science in it. So, then this was the condition at which we in our group we took this particular problem. I wanted to understand why is this happening. Then one of the things that people were thinking those days is probably this whole thing is happening because of the oxygen, because we know zirconium has a strong affinity to oxygen. It can absorb oxygen to a large extent when it is melted, because these are all melted zirconium, copper, nickel, aluminum. You take these elements and then melt them together and form an alloy. During this alloy is made, maybe if it is possible that in the two laboratories where it is made, the conditions were such that in one of the case probably the amount of oxygen is more, which probably is affecting this. To understand this, what has been done is to take an alloy and introduce oxygen into it deliberately in different amounts and try to see whether this oxygen really plays a role. So, that is where this whole work has started, to understand what are the conditions for this nano quasicrystallization process. So, this is one part of the work. Then people have seen that the nano quasicrystal can come in two kind of possibilities. One is you can get a glass and crystallize that glass and get a nano quasicrystal, or you can take the liquid and cool it rapidly by melt spinning technique, rapid solidification, and directly from the liquid also one can get. So, there are some systems such as zirconium nickel manganese, zirconium titanium manganese, zirconium platinum kind of systems, where people could show that yes, you can directly get a nano quasicrystal by just cooling the liquid, whereas in some cases like this kind of alloy, zirconium copper nickel aluminum alloy or zirconium palladium alloy, people could not show that you can get the nano quasicrystalline phase directly, but it always forms as a subsequent step after the glass has been made. First you get the glass and crystallize the glass, and this glass undergoes two-stage crystallization, and the first stage crystallization has always been the formation of nanocrystal. And Inouye has also further showed that a number of elements such as palladium, platinum, gold, silver, these are the elements which can stabilize this nano quasicrystalline phase. That means, if you do not add these elements, you do not get that phase, but if you add them, there is a tendency for the formation of the nano quasicrystalline phase. That means, the alloy composition has an effect. So, we will try to see why it should affect and what are the conditions under which you can make this kind of a thing. And there is also another group, Zing, in 1999, where they also showed that probably titanium also affects it, and this is another case where they showed that in a zirconium copper nickel aluminum alloy, same alloy has been taken and some titanium has been added to it, and they could show that if you do not add titanium, you do not get that phase, but if you add the titanium, you get these nanocrystals, nano quasicrystals. So, we will try to see how these are correlated and what is the ultimate truth behind this whole story. And to understand this, a number of alloys have been taken. One alloy which was chosen is zirconium copper aluminum, which is a standard glass forming alloy. Zirconium with 65% zirconium, 27.5% copper, and aluminum 7.5% is a standard glass forming alloy, and that has been chosen where definite amount of oxygen has been put in. How do we put oxygen into it? How can you introduce oxygen into an alloy? In a known quantities. If you take liquid metal and melt the liquid metal in an oxygen environment, then if you can increase the partial pressure of oxygen, that is one possibility by which you can do it. The technique that has been used in this particular study was to add some copper oxide to this zirconium based alloy. Copper oxide has a much lower melting point, about 1200 degrees. The melting point of a zirconium based alloy is about 1500 degrees. So, when you add this copper oxide, immediately copper oxide melts and then goes into the solution of zirconium, and copper and oxygen become elemental constituents, and they can easily dissolve into zirconium, and one can control the way one can introduce the oxygen, and a number of other compositions have been chosen. I will show you a little later why these have been chosen, and then all these alloys have been studied to understand the basic principles behind the formation of these nano quasicrystalline phase, and they have all been made. The alloys have been melted by arc melting in an argon atmosphere, and then they have been melt spun. You all know by now what is melt spinning, and they have been studied by a number of techniques. What you see first of all is that when you take the three compositions, zirconium, copper, aluminum alloy with different amounts of oxygen, you see all of them show this kind of an XRD pattern. What does that mean? What does this kind of an XRD pattern signify? Preet Browning, anything more than that? These are all amorphous alloy. This particular broad peak always signifies an amorphous phase. So, this alloy which was melt spun is an amorphous alloy in all the three conditions. That means it is a glass. So, a glass has been made in all the three alloys, but when you take these three alloys and heat them in a DSC, what you see is that the alloy with a very small amount of oxygen gives you a single stage crystallization peak, but when you increase the oxygen beyond about 0.4%, you see a 2-stage crystallization. That means what I have told you before, that possibly a nano quasicrystal phase is coming here. So, that has to be proved now, that DSC cannot prove what phase is coming out. It can only tell you that something is coming out, otherwise there will be no peak there. The moment you see an exothermic peak means a glass is crystallizing. So, these two are exothermic peaks. So, suggesting that there are 2 stages of crystallization. And what is also interesting is that if you take a high oxygen alloy and heat it at different rates, if you go to high heating rates, you see that the 2-stage crystallization vanishes into single stage. That means the phase that is forming in this first stage is a very metastable phase, and if you heat it very rapidly, it does not form. So, one has to understand what is that phase that is forming. So, to understand this, what has been done is to take this alloy, heat it to various temperatures, and then take this sample and study it by X-ray. So, this alloy has been heated to different temperatures. You take 400 degrees, 450 and 480 degrees. So, these are the temperatures where the crystal is. For example, if you go back, so 400 degrees is somewhere here, that means where no crystallization has taken place, and 450 is just between the 2 crystallization peaks, and 480 is after the second stage crystallization. So, that means they have been heated in DSC. This is one facility a DSC gives you, that you can heat it in a DSC and then immediately at a particular temperature stop it and quench it. Quench it means cool it rapidly. There is no possibility of quenching into a water or something like that in a DSC, but you can cool it rapidly, so that any further transformation can be suppressed, and whatever transformation that has taken place in the to whatever temperature you have heated, that can be retained. And take that sample which has come out of the DSC and then study it by any technique that you want. For example, here in this case X-ray has been used to study what phase is forming out. So, you can see that X-ray tells you that this is amorphous at 400, but at 450 some crystals have come out, and 480 again exactly the same peaks. That means whatever is coming out in 450 is the same as 480. This is for the low oxygen. In fact, the low oxygen content alloy has shown only one crystallization peak. So, this tells that this particular glass undergoes crystallization by forming this phase, which is called Zr2CuAl. Whereas, when you take a high oxygen alloy, it shows something interesting, that it gives you some peaks at 435, which is the first stage crystallization. When you go to 450, within 15 degrees, all those peaks have vanished. You get new peaks, and which are corresponding to the Zr2CuAl phase, and when you go to 480, again the same peaks will remain. That means this phase which is forming at 435, it is vanishing after 450, and then the same phase persists even if you go to higher temperature. So, some phase is forming, we do not know, but from X-ray we could index them as a quasicrystal, but X-ray is not a technique to find out whether something is quasicrystal or not, because it just gives you peaks. So, we have to find out what is the rotational symmetry, and rotational symmetry can be obtained only if you can do the electron diffraction. So, to do that, what has been done is the electron diffraction, but before that it is also possible to do what is called isothermal heating. Taking both the alloys, one alloy has been heated at 400 degrees centigrade for various timings. You start with 10 minutes, nothing happens, it is amorphous, then go to 15 minutes, you start getting some crystals, and then go to 30 minutes, the crystals become bigger, you get sharp peaks, and then go to 60 minutes, the same peaks persist. So, you can see exactly the same peaks exist there. So, it is again amorphous, giving you to Zr2CuAl. But if you come here, in this case where high oxygen content alloy, it gives you this peaks which are nothing but the quasicrystalline peaks in 10 minutes, and 15 minutes the same peaks are there, but when you go to 30 minutes you do not see those peaks, some other peaks start coming, and those peaks remain when you go to 60 minutes, and those peaks which are coming in the second stage are the Zr2CuAl. That means this particular first alloy crystallizes in a single stage by formation of Zr2CuAl from the liquid or from the glass, whereas in this case the glass gives you first another phase which we are at the moment calling it as quasicrystal only based on the X-ray, and then that undergoes another stage of crystallization which gives you what is called the equilibrium Zr2CuAl. Zr2CuAl phase is the equilibrium phase in this particular composition. And if you do the TEM, what you see here is that at low oxygen levels, what you see is a formation of big crystals which are dendritic type of crystals coming out, and they are all crystalline. How do you know they are crystalline? You can see this pattern, the diffraction pattern obtained from this, which is the periodic arrangement of spots, and periodic arrangement of diffraction spots means periodic arrangement of the atoms in a crystal structure. So that is why this is the Zr2CuAl, and whereas this particular alloy gives you the same alloy which has been crystallized after putting around 0.82% of oxygen and then heated to about 400 degrees centigrade for 10 minutes, it gives you very fine nanoparticles. You can see this scale is about 100 nanometers. That means you have particles ranging from almost 5 nanometers, very small particles, to almost about 50 nanometers. So particles, spherical particles of large size range from 5 to 50 nanometers, and all of them have been confirmed to be the quasicrystalline. How do you know? You count these numbers, they are the tenfold symmetry, you can see. So that tells you that this alloy cannot give you a nano quasicrystal, whereas this alloy can give you. That means oxygen is really doing something, but really we still do not know at this stage where this oxygen is really going and what this oxygen is really doing. To understand that, we have taken this alloy and then studied by what is called an imaging filter. An imaging filter is similar to something like an EDAX in an SEM. Most of you must have heard of energy dispersive X-ray analysis. In SEM we always regularly do it, where you can do what is called elemental mapping. You have a material, two phase material or a single phase material which has a number of elements. You can identify where the element is distributed in that microstructure by what is called the elemental mapping. If you do this kind of elemental mapping, usually dark regions indicate the region where that particular element is depleted, that means its amount is small, whereas the bright regions are those regions where the amount is large. So like that one can do mapping. This is what is called a copper mapping from an alloy containing high oxygen content, and this is an oxygen mapping. Oxygen mapping basically shows you in some regions some oxygen concentration, but unfortunately oxygen atomic number is very small. So whenever you have atomic number very small, it is very difficult to find out this kind of mapping, particularly in SEM. We know that any element less than boron cannot be seen at all. So small atomic number elements cannot be seen because these elements basically the principle behind detecting these elements is by the electrons which are scattered by these atoms, absorbed by knocking out the electrons from the K shell or L shell, and then electrons from a higher shell fall onto that lower shell and some energy is released. The extent of energy that is released will depend on what is the atomic number. Okay, the higher the atomic number, then you will see the bond energies are stronger, and if the bond energies are stronger, the energy of the X-ray that is released is higher. If the energy of the X-ray released is higher, the intensity will be higher. So you can see very bright regions, whereas if the atomic number is very small, the energy is very small, you will not be able to see it. So that is why what we did was we went to another technique called atom probe. An atom probe is basically nothing but a field ion microscope. In a field ion microscope, what you see is that you take a sample in the form of a tip and then subject this particular tip to a high energy, that means high voltage drop with respect to a screen here. When you apply a high voltage from here to here, let us say about 20 kV or so, there is what is called emission. This is called field emission. When you evacuate this whole chamber containing the sample and the screen and then apply a high voltage, the atoms are emitted out of this and then go towards a positive charge, because you make this whole chamber filled with certain gas and that gas gets ionized, and the image of this particular tip can be seen here when these atoms get reflected onto that. So, we can see the image of atomic arrangements on this particular photosensitive plate which is kept there, and this is what is called field ion microscopy, FIM. And this is a technique which has come in about 1950s. People have done a lot of work on try to see dislocations in various atomic arrangements, and also people try to see how stacking faults are present in various materials. So, one can directly see atoms. That is one of the advantage of this field ion microscope, whereas in transmission electron microscope, unless you go to high resolution microscopy, one cannot really see atoms. So, that is one of the advantage of this. And later a new technique has come which is basically a modification of this field ion microscope, which is called atom probe field ion microscope, APFIM. What they do in this technique is that they remove this plate there and put a detector there. Whenever you want to see the image of this tip, you put this plate back, you can see the image, and whenever you want to find out how the atoms are distributed, what is the quantity of a particular element in a particular material, what you do is just remove this plate and allow these atoms to go and fall onto a detector which can detect various elements. How does it detect various elements? Because various elements have different atomic numbers. If you have different atomic numbers, whenever these the atoms are moving from here to here a particular distance, there is a fixed distance between the tip and the detector. The time required for the atom to come from here to here is a function of the atomic number. The higher the atomic number, the heavier the atom is. The heavier the atom, the longer the time that it takes for reaching this. So, from this time of flight, what is called time of flight, one can detect what element is coming, and one can find out all those elements which are coming at a fixed time, and from that one can find out how many such atoms are coming of a particular element. For example, if your material has aluminum and copper, one can find out how many copper atoms are coming and reaching that detector at a particular time, and similarly how many aluminum atoms are coming. Like that one can find out different atoms. And as you keep on sputtering away atoms, this is nothing but sputtering. You are putting a high field, and when you are putting high field, the atoms are sputtered away. So, atoms are sputtered away layer by layer. When layer by layer atoms are coming and joining this detector, and if you can adjust the sensitivity and the time required for the analysis of this detector such that each layer, once it comes, detector immediately recognizes it and then stores it into a computer, and the next layer of atoms come and immediately it detects. What you can do is you can reconstruct the whole of the data that has been collected into the form of a three-dimensional map. So, layer by layer atomic arrangement can be obtained by a three-dimensional mapping of all the data that has been obtained, and you get this kind of blocks. This is nothing but a three-dimensional block. One can even rotate it in a computer and see how the atoms are distributed. Maybe at some point of time, unfortunately this particular course is not about characterization of materials, but at some point of time, if you are interested, I can give you more images and pictures about how to use atom probe microscope to understand various phase transformations which occur. For example, let us say if you want to know that GP zone formation in an aluminum copper alloy, what is this really, what is the composition of the GP zone? It is one of a very astounding questions. People really do not know, because the precipitates are so small that they cannot be observed by IDAX in an SEM. So, if you go to a TEM also, the only way you can image them is only by what is called the strain field, which is around that precipitate, because the GP zones are so small that they cannot, they are very coherent. So, contrast comes only because of the strain contrast. So, it is very difficult to see them, but if this GP zone is nothing but a copper precipitates in an aluminum matrix with a very fine scale of the order of, let us say, 1 nanometer or 2 nanometer size, or even 5 nanometer size. Here you can really see, what you see here is each dot is an atom, each dot is an atom. So, we are able to resolve atom by atom. So, one can see the moment there is a cluster you find of a few atoms, immediately you can identify what is this cluster, what elements are present in that cluster. For example, what you are seeing is this is an amorphous alloy with a small particle inside that, and you can see this is zirconium mapping. These are all what is called elemental mapping. So, a box containing only zirconium atoms, and this is only copper atoms, because one can separate out in a computer each element and then can see clearly how these elements are distributed, and this is aluminum and this is oxygen. And if you look at it, there is a small particle there where the oxygen atoms are concentrated to a large extent, and then the aluminum is less there, copper is less there. So, and if you try to draw a line there and then find out what is called compositional profile, and you can see that here oxygen is enriched in that particular region, aluminum is depleted, copper is depleted, again zirconium is enriched. So, one can really see, and from the amount of it one can find out what is the amount of these various elements. So, one can really do a quantitative study of small particles, very small particles at the atomic level. This is the only technique which can do this, and this is called 3-dimensional atom probe, because you are probing atoms and in a 3-dimensional manner. So, in a 3-dimensional structure one can really see. In fact, people have seen whenever a precipitate comes out, and if you can look at the cross section of this precipitate, and if you want to find it, for example, particularly nowadays people talk about aluminum silicon carbide composites. The moment you put silicon carbide, whoever has studied aluminum silicon carbide, you know that there is a possibility of some kind of a reaction between silicon carbide and aluminum and formation of some Al4, what Al4 Al4C3. Okay. So, there is a possibility of a compound called Al4C3, and sometimes this Al4C3 is such a thin layer you may not be able to see it by any microscope such as SEM, and the only way is possibly by TEM. But in TEM also you will not be able to see really the presence of how much carbon it is, because the carbon cannot be detected so easily by IDAX. Whereas here is a technique where you can really see a layer of carbon atoms and aluminum atoms distributed on a silicon carbide particle, between the silicon carbide particle and the aluminum matrix. And any such precipitates, for example, when in an aluminum magnesium silicon alloy, when Mg2Si comes out on the silicon particles, one can really see that. And similarly, if you add the magnesium to aluminum alloy where silicon carbide is there, everybody says whenever you add magnesium, the wettability of silicon carbide to aluminum gets enhanced. How does it get enhanced? People say it is because of the formation of some spinel. Okay? Everybody who works in composites knows about it, but the presence of such a thin layer of spinel, the only way to find out is by such kind of techniques where you can really see the presence of these atoms, and one can quantify and find out how much of elements that are there. And this is one technique by which we could show that all the oxygen goes into that quasicrystalline particle. And how do we know that this is quasicrystalline? Immediately you can take that sample and put it in a TEM and locate that particular particle there and see that yes, this is the particle that we are talking of is that quasicrystalline particle, and get a diffraction pattern from the particle. So that is why it is very crucial that one technique is not sufficient for everything. Okay. One has to use various techniques as a complementary tools to understand the whole thing. So that is why if you have atom probe in conjunction with a TEM, one can really do a lot of work. and we could show that all the oxygen goes into the particle and gets stabilizes the quasicrystalline particle, whereas there is no oxygen in the glass. This has been shown in a number of cases, and from thermodynamics also one can say this. What happens if oxygen goes into the quasicrystalline phase? Usually we know oxygen is an interstitial element. Whenever oxygen goes into a structure, what it does is it densifies the structure. Icosahedral packing is the densest packing that is feasible. That is why carbon buckyballs are called the densest molecules in the universe. So, if an oxygen goes into the liquid which is nothing but the glass, and the moment oxygen goes to a critical amount, it goes and occupies all the interstitial positions, and once it occupies all the interstitial positions, then the liquid becomes dense, and because of that the icosahedral particles can easily nucleate. And if you look at this free energy, what you see is that without the presence of oxygen, if the oxygen content is less than a critical amount such as 0.4% or so, the free energy of it is much higher than that of the amorphous phase. If I take an amorphous alloy which is nothing but the glass having a certain composition C naught and draw a tangent for that, usually we know from our thermodynamics that any phase that intersects that tangent can come out of that parent phase which is nothing but the glass here, but if the phase free energy is above that of the tangent, then it cannot nucleate, because there is no driving force for that phase to form. For example, if you look at the icosahedral phase or the quasicrystal with carbon oxygen content less than 0.4, its free energy is such that it is above this tangent. If it is above this tangent, that phase cannot nucleate, but the moment you put certain amount of oxygen greater than a critical amount, its free energy comes down, and the moment it comes down, it intersects this particular tangent, and then immediately there is a certain driving force which is shown by delta Gi, and that driving force drives the formation of the quasicrystalline phase. And the moment quasicrystal forms, then there is a equilibrium between the quasicrystalline phase and the amorphous phase. But if you carefully look at this tangent, which is the tangent between the icosahedral phase and the amorphous phase, this tangent intersects this equilibrium compound which is nothing but the Z2CuAl, and the free energy of the Z2CuAl is lower than that of the two phase mixture which is nothing but the quasicrystal and amorphous. So, as a result, a two phase mixture of quasicrystal and amorphous has still a higher free energy than the Z2CuAl. So, that means ultimately if you hold it for a long period or heat it to a higher temperature, what happens is that this two phase mixture of amorphous phase plus icosahedral phase will ultimately transform to the equilibrium Z2CuAl, and this is what exactly happens when you look at the mechanism of its formation. If the oxygen content is below a certain value, what you see is that amorphous phase gives you Z2CuAl, and this Z2CuAl grows, and finally you get a simple Z2CuAl, and this is what is called polymorphous crystallization. What is polymorphous crystallization? I think we talked about it in the last class. Basically, if you look at the free energy composition diagram and look at an amorphous phase which is having a free energy like this, this is the free energy versus composition, and if you look at an intermetallic compound which has something like a Z2CuAl, amorphous phase having certain composition, if it transforms to the crystal having the same composition which is nothing but Z2CuAl, in this particular case we call this as what? Polymorphic transformation, because the one phase parent phase which is nothing but a glass here is transforming into another phase having the same composition, but a different crystal structure. The only difference is the crystal structure, but the composition is the same, and this is what is called polymorphous polymorphous crystallization or polymorphic transformation, and that is what is happening if the oxygen content is less than a certain amount. Otherwise, if the oxygen content is more than certain value, critical value, what you see is a first stage of crystallization gives you quasicrystal whose composition is different from that of the amorphous phase. This has been proved by atom probe. We have shown that the composition of the quasicrystal is different from that of the background matrix, and we have also shown from the thermodynamics earlier that this is the composition of the amorphous which we are starting with C naught, and the composition of the icosahedral phase is this, which is different from this C naught. So, when a phase having a different composition comes out from a parent phase, we call this as primary crystallization. A phase having a different composition comes out of the parent phase, this is called primary crystallization, and in such a case you will always have, for having the mass balance, you will have some volume fraction of the product phase and some volume fraction of the parent phase. We talked about in the last class that unless you have both the phase coexisting, it is not possible to have a mass balance if the two phases have a different composition, and that is what we talked in the last class, where we said a volume fraction of the product phase multiplied by the composition of the product phase plus the volume fraction of the parent phase after the formation of the product phase multiplied by the composition of the parent phase after the formation of the product phase is equal to the starting composition C naught. And what is the volume, what is the composition of the product phase here? The composition of the product phase is this, the point E that you are seeing. And what is the volume what is the composition of the amorphous phase after the product has formed? It is this F. The starting composition is C naught, but once the icosahedral phase forms, immediately there is a equilibrium between the icosahedral phase and the amorphous phase, and the equilibrium composition of that amorphous phase in equilibrium with the icosahedral phase is nothing but this F and not the starting C naught. So, that F is this composition of the parent phase that we are talking here, and that if you multiply by the volume fraction, then you can see the total number of atoms can be balanced, otherwise you cannot balance the atoms. So, and we know that one cannot create new atoms or one cannot destroy already existing atoms. So, there one can only do is one can distribute the atoms between two phases. So, some of the A atoms go into one phase and some of the A atoms will go into the other phase, so that the overall number of A atoms is same as the starting material, and that is what happens here, that you get a quasicrystalline phase with a different composition, and after some time what you see is that some ZR2CuAl phase forms at the interface between this quasicrystal and the amorphous phase, and then starts growing by something like a peritectic type of reaction. That means the amorphous phase plus quasicrystal gives you ZR2CuAl. Okay. This is similar to a peritectic type of a reaction. Only difference is, what is a peritectic reaction? Can somebody tell me what is a peritectic reaction? Liquid plus solid gives another solid, but here we are not talking of liquid plus quasicrystal giving another solid, but amorphous plus quasicrystal giving another solid. So, this is actually to be called as a peritectoid type of a reaction, where you have a solid plus another solid giving you a new solid. All the three of them have a different compositions. Okay. And finally, you get the ZR2CuAl, and so if you look at the final microstructure, both of them have similar microstructure. You have the grains of ZR2CuAl, but this particular alloy goes through a second stage, whereas this whole thing undergoes a one stage crystallization. So, this is how we see the formation of nano quasicrystal. So, we clearly now know that it is oxygen which stabilizes this nano quasicrystalline stage, but at the same time one more important point that one has to know is oxygen is not sufficient. How do you know that? So, this is another study which has shown that oxygen is not sufficient. What does it say? So, here what has been done is, we have taken zirconium copper alloy without any aluminum in it and put again same amounts of oxygen, You keep on increasing the amount of oxygen and see what kind of phases form, and you see amorphous phase can be obtained at high oxygen levels, and take that and then do DSC. You again see here, instead of 2 crystallization peaks, you see only 1 crystallization peak. 1 crystallization peak tells you that it transforms in one stage, and what does it transform to? It transforms to Zr2Cu. There is no aluminum here, it forms only Zr2Cu phase. So, whether it is a high oxygen or a low oxygen, this is a low oxygen, this is a high oxygen. So, an amorphous phase goes to a Zr2CuAl without any intermediate step of any icosahedral phase. So, this clearly tells you that for an oxygen to stabilize an icosahedral phase, one needs to have a certain environment. So, if you have zirconium, copper, aluminum kind of a combination where the sizes of the interstices will be bigger, where oxygen can easily go and then make the icosahedral phase stabilized, whereas if you do not have aluminum there, then you will not have such a thing happening. So, one can talk in terms of what are the criteria for such formation. This is one study. The other study to show what are the conditions for the formation of this icosahedral phase, nano icosahedral phase, is lot of people have shown, for example, Inoves group, that palladium, platinum, some kind of elements like that can stabilize a formation of a nano quasicrystalline phase. So, what has been done here is that this is a standard composition which people have been studying for quite some time, where you have about 65% zirconium and copper about 7.5, aluminum about 7.5, nickel 10% and palladium 10%. And the understanding at that time is that this nano icosahedral phase will come out, nano quasicrystal will come out only when you have a multi-component system, and unless you have a large number of elements, you will not get this kind of a phase, is some myth, I would say, was existing those days. So, we again have wanted to look at it more closely, and what we did was we tried to eliminate various elements systematically from this base alloy by eliminating. For example, here you can see in this nickel has been removed, in this aluminum has been removed, and in this both nickel and aluminum have been removed. Again overall composition has been maintained the same. Palladium is again 10%, you can see in all of them. Zirconium is again 65% in all of them. Only thing is you have removed certain elements and maintaining the composition the same. And similarly, you remove aluminum here and again remove aluminum and nickel here, and see that in various cases what kind of DSC that you get. All these alloys, if you look at the X-ray, they are all amorphous when you make the alloy, and when you do DSC, you always get 2-stage crystallization, always you get 2 peaks, always, and that means probably there is an icosahedral phase. And if you do take this alloy to the first stage and quench it, you see that in all the cases you get an icosahedral phase, excepting in one case, which is zirconium 65, copper 25, palladium 10, where you get another crystalline phases, basically because in this alloy the 2 peaks are very close to each other. You can see here, this is the alloy for which this is the XRD pattern after the first stage. So, because these two are overlapping with each other, when you heat it to this temperature, already the second stage crystallization starts. So, you cannot really suppress the second stage crystallization, that is why some crystals come out, otherwise in all the cases you get an icosahedral phase. And to confirm that, what we can do is that we can heat it to the first stage and put it in a TEM, and you can see all these fine nanocrystals. These are all nano quasicrystals. How do you know that in all the cases you have either the 10-fold or the 3-fold showing the quasi periodicity? You can look at this 3-fold and see the distances, they are not equal in any direction. Look at any direction, they are not equal, and similarly here also you see this distance and this distance, they are not the same, and that is what is an indication of this is a icosahedral phase. So, you can get nano quasicrystalline phase here again in all the compositions including a binary. This is from 5 component, 4 component, 3 component, and even a binary also has been done. I will show you a little later that even when you go to binary also one can get it. So, this is one proof that yes, you do not need any multi component system. Then in such a case, what is that is making these alloys to become nano quasicrystalline. So, that is something which one has to understand. To understand this, people have done much more work in our group, and you can see this is one such detailed work showing the formation of the icosahedral phase. This is what is called high resolution microstructure, showing each white spot here again is an atom. Okay. So, you can see really atomic images in a high resolution electron microscopy, and clearly find out what is the difference between the amorphous phase and a icosahedral phase. You can see amorphous, all the atoms are randomly arranged, and so it is this is basically trying to take a region like this, and then looking at a region where there is an interface between the amorphous and the quasicrystalline particle. So, such a region, if you look at it, this is a particle which you are looking at, and this is the amorphous matrix. So, you have a matrix of amorphous in which these nano quasicrystalline particles are embedded, and you are looking at them, and this is one individual nano quasicrystalline particle, and where you can here also again in any particular direction, if you carefully look at it in a line, you can see you will never see periodic arrangement of atoms. You will see only quasi periodic arrangement of atoms. This is another way to confirm that this is a quasicrystal, and one can study what is called the kinetics of such formation of these nano quasicrystalline phase. What one can do is what is called isothermal heating in a DSC. What we know is that you know that in a DSC, which I have shown you earlier, that one gets 2-stage crystallization. If you are getting a 2-stage crystallization, what you can do is you heat it to a particular temperature, hold it at that temperature for a long time. As you keep on holding the amorphous phase heated to a particular temperature, hold it for a long time, this amorphous phase, if it is unstable or a metastable there, it should transform to a phase, whichever phase it is. In this particular case, the first stage is a nano quasicrystalline phase, so it will transform to that. So, when it is transforming, you can get a peak, exothermic peak, as a function of time, and you can see here this is the exotherm as a function of time at various temperatures. As you, at very low temperatures, less than about 698 or so, the temperature is so low that the activation barrier for the formation of that phase is so high that you do not get any exotherm. That means there is no formation of a nano quasicrystalline phase, but as you keep on increasing the temperature is high enough to overcome the activation barrier, because we know that whenever a quasicrystalline phase, whenever a glass, if this is a glass, has to transform to a nano quasicrystalline phase, you have an activation barrier. If you keep on increasing the temperature, you are able to provide more and more energy to overcome that activation barrier, and one can easily get the formation of the nano quasicrystalline phase. And how do you know that it has formed? You can know from the peak. If there is a peak, exothermic peak, that will give you an idea of that the phase has formed, and from the area under the peak one can find out how much of this phase transformation has taken place, and that is what one can plot, what is called fraction transformed as a function of time. Okay, that the amount of phase that has formed from the glass, this is just one particular case of glass to a quasicrystal, but this is a technique which is known for ages, which people call Johnson-Mel-Avrami equation. If you have done any kinetics, you will come across this particular kinetics, what is called Johnson-Mel-Avrami expression, where we know that any transformation as a function of time at a given temperature is like an S curve. This is called sigmoid curve. What is the significance of that? It says that there is always an incubation period. Up to certain period there is no transformation, and after that transformation starts, that is an indication of nucleation has taken place, and then now growth is taking place, and it keeps on increasing and finally becomes 1 means 100% transformed after certain time. that means this is a start of transformation, this is the end of transformation, and as you keep on increasing the temperature, the start and end of transformation occur at a shorter period. That means the kinetics have been enhanced, the same transformation occurs in a shorter period, and you get the total transformation complete in a very short period, and this is what is one can do, and one can take all these start and end of transformations at various temperatures and plot what is called a TTT type of a diagram, and from that one can see what is a region metastable amorphous, amorphous plus icosahedral, and nano icosahedral phase. This is what similar to what is our TTT diagram for austenite to perlite. How do you get austenite to perlite TTT diagram? Exactly by this technique. You take austenite, quench it to a certain temperature, hold it for over a period, and find out how much of perlite is forming, and from that you identify what is the start of perlite formation, end of perlite formation, and at various temperatures if you do this, ultimately you get this C curve. Exactly here one can do, and one can do what is called Avrami experiment, which gives you what is called the growth conditions, what is the rate of growth, and from this Avrami exponent one can talk about what kind of transformation it is. Usually if the Avrami exponent is about 2 or 2.5, we can say it is always a primary crystallization. If it is more than that, then if the Avrami exponent, if it is equal to around 4, we can say it is polymorphous crystallization. So there is a lot of, when you come to kinetics, when Professor Pobby teaches you kinetics, you will know all this, that from the Avrami exponent one can find out what kind of transformation it is. So from this we can prove that this is a primary crystallization kind of process and not a polymorphous kind of process, which is another controversy that was existing in this particular case. And similar thing has been proved also in a binary case. What you have seen earlier is a 5 component alloy here, and now you can see in a small simple binary case that you can get an icosahedral phase like this, and all these studies can be repeated and again show that even in a binary case it is a primary crystallization, and from this one can prove that a multi component alloy is not essential for the formation of a nano quasicrystalline phase. So this is one of the study to show that what are the conditions for the formation of nano quasicrystalline phase. We will stop here and continue and look at what are the other conditions which are required for the formation of this particular nano quasicrystalline phase in a metallic matrix to get this kind of composites which have much higher strength than the either the amorphous phase or the quasicrystalline phase, and we will look at it in the next class. Thank you.